Welcome to EDU World Space.
So in this video, we're going to work through question 110 from chapter 20, which says a proposed two-step mechanism for the destruction of ozone in the upper atmosphere is given below. So right here, where the red atoms are oxygen and the blue atoms are nitrogen. And then in question A, we're asked, what is the overall balanced equation for the ozone destruction reaction? So let's take this image and translate it into a balanced equation, or two steps in a balanced equation, and then we'll add those two steps together to get the overall balanced equation. So this is O3, this is NO, and this is NO2. So let's go ahead and write this out. So we have O3 plus NO yields NO2 plus O2. Let's take a second to check if this first reaction is balanced. We have 4 oxygen atoms and 2 nitrogen atoms on both sides, so we're good. And then the second step is NO2 plus O yields NO plus O2. And again, we have 3 oxygen atoms on both sides and 2 nitrogen atoms on both sides, so that's balanced. So let's add them together to get the overall reaction. Now, NO appears on both the reactant and product side, and so does NO2. So those two are going to cancel out, and we're left with O3 plus O yields 2O2. So that's the answer to A. That's our overall balanced equation. And then in B, we're asked which species is a catalyst. So a catalyst is something that participates in the reaction, but is reproduced at the end of the reaction. So it's not used up by the reaction. We have our catalyst at the beginning, it is used to further the reaction, and then it's reproduced at the end. So in this case, that would be NO. So NO is reacting with ozone in the first step in the reaction mechanism, but in the second step, it's being produced. So the species that's a catalyst is NO. And then we want to know which species is an intermediate. So an intermediate is a species that is produced by one step in a mechanism and then later consumed in another step in the mechanism. It doesn't appear in the overall equation, same as a catalyst doesn't appear in the overall equation. So which species is an intermediate? Well, NO2 is produced in the first step in our reaction mechanism, but is then consumed as a reactant in the second step of the reaction mechanism. So which species is an intermediate? That's NO2. And then in D, we're asked, what is the rate law for this mechanism if the first step in the mechanism is slow and the second step is fast? So the rate law for reaction depends on the slow step in the mechanism. So you take the slow step in the mechanism and you have your rate constant times your concentration of reactants raised to their stoichiometric coefficients or their molecularity. So in this case, our slow step is the first step in the reaction. So our reactants are O3 and NO, and their stoichiometric coefficients are 1. So our rate is equal to our rate constant K times O3 concentration times NO concentration. And finally, E. One of the concerns about the use of freons is that they will migrate into the upper atmosphere where chlorine atoms can be generated by the reaction where CCl2, F2 plus light gives us CF2Cl plus a chlorine atom. Chlorine atoms can also act as a catalyst for the destruction of ozone. The first step of a proposed mechanism for the chlorine-catalyzed ozone destruction is Cl plus O3 yields ClO plus O2. Assuming a two-step mechanism, propose the second step in the mechanism and give the overall balanced equation. So let's use our other ozone destruction mechanism as guidance. So you can kind of see some parallels between the first step in this mechanism and the first step in our other mechanism. So the first step in our other mechanism was O3 plus NO yields NO2 plus O2. And in this one, we have O3 plus Cl yields ClO plus O2. So what's changed? Instead of NO, we have Cl. And instead of NO2, we have ClO. So since NO was a catalyst and NO2 was an intermediate in the overall reaction, then in this chlorine catalyzed mechanism, chlorine was the catalyst and ClO is the intermediate. So we can write our second step in the mechanism using the second step in the other mechanism as guidance. So we have our intermediate, which is ClO, and we're going to react with an oxygen atom in the same way that we did in the first mechanism. And then we're going to produce our catalyst, which was Cl, and our other product is O2. So that seems like a valid mechanism, but let's add them together to get the overall reaction. So again, our catalyst appears both as a reactant as a product, and our intermediate appears both as a product and a reactant. So those are going to cancel out. And our overall reaction is actually the same as it was for the other mechanism. It's O3 plus O yields 2 O2.